In this video, we'll be looking at the Fibonacci interview question. My name is Larry, and this is Digital Logic. To get started, you'll need to download the project from GitHub. A link is in the description below. I've also included a link to the introduction video to the series, which will walk you through setting up your development environment. With that out of the way, let's get started. So I've already got the project open in IntelliJ, so I'll open up the project browser and find the Fibonacci class. For this challenge, you need to write a function that will produce the nth number within the Fibonacci sequence. The first two numbers within the Fibonacci sequence are 1. After that, the next number is the sum of the previous two. This is what the Fibonacci sequence looks like. And here are some examples of the expected output for the provided input. Once you have a solution that you're ready to test, you can press Ctrl-Shift-T to open up the testing class. Then click on the little icon next to the class name to run the test. The testing class will pick up any public method that you define that matches the expected signature. So you can provide multiple solutions, and the testing class will test all of them. So go ahead and pause the video here and try to come up with a solution to this challenge. When you're ready to continue, come back here and we'll walk through a couple different solutions. Welcome back. So I'll start by creating some extra space. And then I'll delete the return 0 statement. And then create a new long array. Catch equals new long array and set its length to n+1. Next, I'm going to store the first two values in the Fibonacci sequence in the catch. So catch at 0 equals 0, and catch at 1 equals 1. Next, create a for loop. In at I equals 2, I is less than or equal to n, and an increment I. Now catch at I equals catch at I minus 1 plus catch at I minus 2. So what this will do is generate our Fibonacci sequence and store it in the catch array. Now we just need to retrieve the nth value. So return catch at n. Press Ctrl-Shift-T to open up the testing class and then run the test. And the solution has passed the test. Make sure to have Show Passing checked so that you can see the passing test as well as the failing ones. So nothing is wrong with the solution. It does work and it's pretty efficient. But it does require us to create an array with n+1 elements in it, when we really only need to know the last two elements in the Fibonacci sequence to generate the next number. So it would be far more efficient memory-wise if we only store the last two values that were calculated. So I'm going to create a new method, and I'll name it Fib OP. So go ahead and pause the video here and try to come up with a solution that is similar to the one that we just created, but only requires to store the last two elements within the Fibonacci sequence. Welcome back. So one way that we can solve this problem would be to create two variables to store the last two values within the Fibonacci sequence. However, when we calculate the next value, we'd have to shuffle that in and get rid of one of the older values. But I'm going to show you an easier way to do this. So create a new long array, catch equals, and I'm going to initialize it to two values, 0 and 1. So this array contains the first two values within the Fibonacci sequence, fib of 0 and 1. Next, create a for loop, in at I equals 2, I is less than or equal to n, and then increment I. So this is where the magic happens. Catch I percent 2 equals catch 0 plus catch 1. Take a moment to try to understand what's going on in this code. The percent symbol is the modulus operator, and it returns the remainder of a division. With each iteration of this for loop, we need to alternate the position that we store the next value within the catch array. When I is even, the next value that we store is at position 0 within the catch array. When I is odd, the next value is stored at position 1 within the catch array. This alternating of the index ensures that we always overwrite the older value that we don't care about anymore. Now we just need to return the Fibonacci value of n. So return catch, but which index should we retrieve? If n is even, we'd retrieve index 0. If it's odd, 1. So n%2. Press Shift F10 to rerun the test, and it passes. So next we'll look at the recursive solution. I'll start by creating a new function, and I'll name it recursive. First thing is create our termination condition. So if n is less than or equal to 1, return n. Next, I'm going to return recursive n-1 plus recursive n-2. And that is it. Press Shift F10 to rerun the test, and it passes. However, before we get too excited about the solution, take a look at the runtime for this solution. Now the runtimes that are recorded here are not super accurate. So if you're only a few milliseconds, 3 or 4 milliseconds difference, you can't really say one solution is faster than another. However, in this case, there's a clear difference in performance. The recursive solution took nearly half a second, where the other solutions took 2 milliseconds at most. So the question is, why is this solution so much slower? The simple reason is because it does a lot of repetitive work, and the amount of repetitive work that it does increases drastically as the value of n increases. This is something that I'll cover in more detail later on when I cover time complexity, and then again when I cover dynamic programming. If the solution took a long time on your computer to run and you don't want to have to wait for it to run again, you can disable it by adding the disabled annotation right above the function. Shift F10 to rerun the test, and you can see it's no longer being tested. All right, so how can we implement a recursive solution that isn't painfully slow? One way to do this would be to use a technique called memoization, where we use an internal catch to record intermediate values. I know that may have sounded pretty complex, but it really isn't. All we're going to do is use an internal array to store intermediate values. So I'll create a new function, and I'll call it Recursive Memoized. And then create another function. This time it's going to be a private static function, and I'll give it the same name, Recursive Memoized. Only this time it's going to take 2 parameters, an init n, and then an array. And now let's go back to the first function and create a new array, memo equals new long, and set its length to n+1. And now return recursive memoized, pass in 2 parameters, n and memo. Now let's go back to the second function and implement the recursive solution. So first define the termination condition. So if n is less than or equal to 1, return n. Now we need to check if memo contains the computed value for n. So if memo at n equals 0, then we haven't computed this value yet. So memo at n equals recursive memoized, pass in n-1 as the first parameter, and then memo as a second parameter. And then add that to recursive memoized, n-2, and then pass in memo. Now we just need to return the value at memo n. Press Shift F10 to rerun the test, and it is passing. And look how long it took to execute this time. So it's a massive improvement in performance. So we've seen how an internal catch can be used to speed up a recursive solution. So in this next solution, I'm going to show you how you can externalize the creation of this catch. This way, the algorithm itself doesn't have to provide it. Now this is going to be more advanced code than what we have looked at so far. So I'm going to start out by creating a new private function. And I'm going to use generics in this one. So we'll have two types. T is the input type and R is the return type. And it's going to return a type of function. That is T and R. And I'm going to call this function Memoizer. And let's import the function class real quick. All right, so now this method is going to take a single parameter, and it's going to be of type function. It'll have the same generic signature. Now create a new final map of type T and R, and name it memo equals new hash map. So this is going to function just like the memo did in the previous solution, just as an internal catch. So now we're going to return a new lambda with a single parameter of type T. Now we need to check if the value of T has already been stored in the memo. So memo.contains key T. If the memo doesn't contain this key, then we need to compute it by running it against the function and then taking the result and storing it in the memo. So memo.put T, then func.apply T. And then finally return this computed value from the memo. Notice the similarities between this function and the previous solution. The main difference here is that we're externalizing the logic that deals with maintaining and retrieving the intermediate values. So now let's put it to use. Create a new public static function of type integer and long. And we'll call it memorized fib equals. And here we're going to call our memorizer and then pass in a lambda. Let's add in the termination condition. And then return. And because this is a static property, we need to call the class name dot memoized fib dot apply n-1 plus Fibonacci dot memoized fib dot apply n-2. And we still have an error, and it's because we have to cast the value of n to a long. Press Shift F10 to rerun the test, and it is passing. Notice that the Memoized Fib solution only took about 2 milliseconds to run. One of the big disadvantages of a solution like this in Java is that we cannot call the Memoized Fib function directly because functions in Java are not first-class citizens. So what we get instead is an object that we have to call apply on to actually execute the function part of it. So I'll just create a static initialization block real quick as an example, and then call Memoized Fib, and then apply, and then pass in the value that you want to compute. Anyway, that is it for this video. If you like this video, then please like, share, subscribe. If you want to support the creation of these videos, then check out my Patreon page. A link is in the description below, and I'll see you in the next video.